So the next topic we want to discuss is the topic of fairness and bias. So machine learning, as we saw, is augmenting and sometimes replacing human decision making in many situations. For example, whose loan gets approved, to what neighborhoods police officers are deployed, who gets pre-trial release or parole. But machine learning models can perpetuate societal bias. Consider the example of an algorithm to predict whether criminal defendants are likely to reoffend, which essentially determines whether they can be released before trial. It could well be that such a system picks up the racial or gender prejudices of human judges from the examples in the training set. Designers of machine learning systems have a moral responsibility to ensure that their systems are in fact fair. In regulated domains such as credit, education, employment, and housing, they have a legal responsibility as well, in addition to their moral responsibility. But what is fairness? So there are multiple criteria, and these are the 6 most commonly used concepts. First one is individual fairness. So that's a requirement that individuals are treated similarly to other similar individuals, regardless of what class they are in. The next concept is group fairness, a requirement that 2 classes are treated similarly, and this can be measured by some summary statistic. The next concept is fairness through unawareness. So if we delete the race and gender attributes from the dataset, then it might seem that the system can't discriminate on those attributes. Unfortunately, we know that machine learning models can predict latent variables, such as race and gender, given other correlated variables, like zip code and occupation. Furthermore, deleting those attributes makes it impossible to verify equal opportunity or equal outcomes. Still, some countries, like Germany, have chosen this approach for their demographic statistics. The next concept is equal outcome. The idea is that each demographic class gets the same result, which means that all demographic classes have demographic parity. For example, suppose we have to decide whether we should approve loan application. The goal is to approve those applicants who will pay back the loan and avoid those who will default on the loan. So demographic parity says that both males and females should have the same percentage of loans approved. This approach favors redress of past biases over accuracy of prediction. If a man and a woman are equal in every way except the woman receives a lower salary for the same job, should she be approved because she would be equal if not for historical biases that essentially led to her lower salary? Or should she be denied because the lower salary does in fact make her more likely to default? Next concept is equal opportunity. That's the idea that the people who truly have the ability to pay back the loan should have an equal chance of being correctly classified as such, regardless of their sex. This approach is also called balance. It can lead to unequal outcomes and ignores the effect of bias in the societal processes that produce the training data. Finally, equal impact. The idea that the people who truly have the ability to pay back the loan should have an equal chance of being correctly classified as such. So, This goes beyond equal opportunity in that it considers both the benefits of a true prediction and the costs of a false prediction. So let's talk about these issues, in a given example. Compass is a commercial system for recidivism or reoffense scoring. So it assigns a defendant in a criminal case a risk score, which is then used by a judge to help make decisions. Is it safe to release a defendant before trial, or should they be held in jail? If convicted, how long should the sentence be? Should parole be granted? Given the significance of these decisions, the system has been the subject of intense verification. So Compass is designed to be well calibrated. All the individuals who are given the same score by the algorithm should have approximately the same probability of reoffending, regardless of race. For example, among all people that the model assigns a risk score of 7 out of 10, 60% of white and 61% of black reoffended. The designers claim that it meets the desired fairness goal. On the other hand, Compass does not achieve equal opportunity. The proportion of those who did not reoffend but were falsely rated as high risk was 45% for blacks and 23% for whites. In the case State versus Loomis, where a judge relied on Compass to determine the sentence of the defendant, Loomis argued that the secretive inner working of the algorithm violated his due process rights. The Wisconsin Supreme Court found that the sentence given would be no different without the use of Compass in this case. However, it did issue warnings about the algorithm accuracy and risk to minority defendants. So is it possible for an algorithm to be both well-calibrated and equal opportunity? Or is that something that's impossible? If the base classes are different, then any algorithm that is well-calibrated will not provide equal opportunity, and vice versa. So how can we balance the two criteria then? Equal impact is one possibility. In the case of Compass, for example, this means weighing the negative utility of defendants being falsely classified as high risk and losing their freedom versus the cost to society of an additional crime being committed, and finding the point that optimizes the trade-off. Now, this is not easy, obviously, because there are multiple costs to consider here. For example, for the defendant who is wrongfully held in jail, he suffers a loss. Same as the victim of a defendant who was wrongfully released and reoffends. But beyond that, there are also group costs. Everyone has a certain fear that they will be wrongfully jailed, will be the victim of a crime. If we give value to these fears in proportion to the size of a group, then the utility for the majority may come at the expense of a minority. Sometimes fairness means that we should reconsider the objective function that we're trying to minimize, not the data used to train the algorithm. For example, in making job hiring decision, if the objective is to hire candidates with the best qualification in hand, we risk unfairly rewarding those who have had advantageous educational opportunities throughout their life, which will enforce class boundaries. But if the objective is to hire candidates with the best ability to learn on the job, we have a better chance to cut across class boundaries and choose from a wider pool. Of course, this requires defining which classes deserve protection. Is it race, color, religion, sex, national origin, disability, or family status? Maybe pregnancy, maybe veteran status. Are these all fair classes to use when discussing fairness and bias? Even in the absence of societal bias, sample size disparity can lead to biased results. In most datasets, there will be fewer training examples of minority class individuals than the majority class individuals. Machine learning algorithms give better accuracy with more training data. So that means that members of minority classes will experience lower accuracy. The constrained model may not be able to fit both majority and minority classes. So in that case, most of the predictions will be to better fit to the majority class members. Bias can also come into play in the software development process. Engineers who are debugging systems are more likely to notice and fix those problems that are applicable to themselves. For example, it's difficult to notice that a user interface design won't work for colorblind people unless the engineer doing the debugging is actually colorblind himself. Or that a language translation to a given language is incorrect unless the person doing the development doesn't speak the language. So how can we avoid these biases? First, we have to understand the limits of the data we're using. Some researchers suggested that datasets should come with annotation, discussing its fitness for use. This is similar to the data sheets that come with electronic components, like resistors, for example. They allow engineers to decide what components to use and where. In addition to the data sheets, it's important to train engineers to be aware of issues of fairness and bias in school and on the job. A study found that only 18% of researchers in AI and 20% of AI professors are women. Black AI workers are less than 4%. So diversity could be increased by programs earlier in the pipeline, maybe in college or high school, and by greater awareness at the professional level. The second idea is to debias the data. So oversample from the minority class to defend against sample size disparity. The third idea is to invent new machine learning models and algorithms that are more resistant to bias. The final idea is to let the system make initial recommendations that may be biased, but then train a second system to debias the recommendation of the first one. So all of these ideas are important. Just make sure in general to ask yourself, how do you make sure that the systems you build will be fair? How to create an environment that fosters the development of a diverse pool of software engineers? How to optimize for an objective function that incorporates fairness? Make sure to examine your data as an engineer for prejudice and for correlation between predicted attributes and other attributes. Okay, so these are all general recommendations. Hopefully You can get some more information from the textbook. See you in class.